Americans was living at, and he was from Iraq. He's like, oh, American. Oh, I'm like, dude, you're making this weird now. Like, now you're just making this weird. Oh, yeah. You gambling in that?
What? A little bit less credit, a little bit. Wait, love credit?
Yeah.
I got you guys. I'm going all out. Matter of fact, what's a little $150? That's a little bit of that.
I feel loud. Like, if we were ever on a host, like, a party day, if it's like, the profit.
They're doing it right now. It's not right now, but they're doing it.
That's allowed.
Yeah. They don't get it.
Oh, just like a chip tonight.
Yeah. I need to be fair.
You can get what candy.
Oh, okay.
Cool. I mean, I know, like, in high school, like, middle school, it really, like, we weren't allowed to play basketball. Like, we were playing Go Fish. And, like,
Yeah.
I just played Go Fish.
Yeah.
I used to get home with real money. Yeah, no, I love to be like,
Yeah.
right? I was all Leo, and I was like, I was gonna choose it.
You made roulette.
Yeah, but here's the thing. I was like, oh, you.
I've been trying to get these off to go for a year.
I mean, I got like,
I remember you telling me you got it there.
Yeah. Pretty good. How about you? Pretty good. Yeah? Like that. Cool. Pretty nice.
Yeah, they're kind of crazy sometimes.
Yeah.
A bit more crazy than fun. Like infectious too.
oh, work for
Our classes back.
they're controlling me to get my
Get back into it.
I thought it started at 12.
Nothing I was looking for. I was just
I
understand.
did it.
Well, yeah.
I was making adding as well. I'm doing architecture. Let's take it.
Okay.
I'm good at that.
Just got to figure it out.
I don't do that. 0.4 acres.
Look at that.
Oh, just by the way, we do have this remote until 2, so you're totally allowed to go over.
Okay, cool.
Yeah, and I think we might talk about it later.
Okay, that's cool.
Yeah. Do you have anywhere you need to be, or?
Nope.
Oh, okay. I don't want to, like,
Good.
push it back and, like, you're late for anything. Maybe next week. We're a little more time. Give a few notices, and I need to say it now or else I'll forget.
Okay. In that case, they didn't just about to get it.
I just, like, I take, like, at everyone. No.
Oh, I don't care. Oh, it was 11 p.m. I'm like falling asleep. That's just, like a stop in mercy at everyone. Why isn't one responding? Are you kidding me? Something like that. All the time.
It could have been me. I do that.
I did not at everyone in the middle. I did that in the middle of the day.
Well, I
It's just kind of awkward because there's something I should do.
that's right.
Thank you. Did it work?
No, it says it looks like it's trying to check in someone else, and that says it's already in the net.
What? No. That's
Oh, it's the text one.
Oh, yeah.
We don't have a swipe. Okay, we only have like 2 items in the 3, kind of. Like 4 and a half, kind of 4. Yeah. Yeah. We're the computer science club, technically.
Really?
Yeah.
Oh, cool. I was looking to figure out which one.
That's yeah, I guess it's not super clear with the acronym. Association for Computing Machinery and Society for Women. I think we're the.
That's a long one.
Yeah, that's what we just figured.
Council, association,
Yeah, something like that. It's insane. It's insanely long.
You have a district?
Yes, we do. Yes. I should probably post more posters. but I can send it again. And are you in?
Oh, yeah.
Oh, was it already in business?
I don't think the link was valid. Hey, you know what, Diego?
Yep.
I'll make you do something. Could you send, are you in Ben's Discord?
Yeah.
McCamish, could you send the ACMW Discord link? Because I think when I sent it, it was like invalid. Somebody said it was invalid, or maybe it's like valid.
Yeah, we close that up. I should still leave this time.
Is it okay if I take photos, by the way? Is that okay?
Okay with me.
Okay. I need to post about stuff more. Okay, it's past 12. So I'll do some announcements. Okay. Hi. Thank you everybody for joining. Super excited. I'm very happy to have Dr. Macias here. Long time in the making. What that was. And I have a few announcements before we start. So next week we will not be meeting because it is Veterans Day on Tuesday and there's no school. I don't want to be here, so there's no fun meeting. For those who are participating in the ICPC, I will need to look up the date, but in order to participate, not a requirement, I need you guys, your teams to submit, I'll send the link, like practice questions. It's just to show that like you know how to use the system before starting the event. I'll find a date for that, but because I will also be gone next week, so there's no club meeting and I'll be gone, so please do that, guys. Spread the word to your teammates. Hi, Connor. So not next week, but the week after that, we have our Mesa event. There will be food. Oh, you got the food thing in, right?
I sent it in.
Oh, you did? Okay. Was it Jersey Mike's?
Yes, but like.
Okay, so we got the fancy Jersey Mike's. So there'll be food provided. If you guys don't know what Mesa is, it's, oh gosh, I forgot what it stands for, but basically it's going to be volunteering. A kind of an intro to a volunteering opportunity this spring. Mesa, if you guys don't know, is a organization that goes to high schools and middle schools, and they help students work with Arduinos and build little projects. Super fun. It always looks good on resumes, and I think they have internship unpaid, like internship opportunities. They do enough hours. There'll be food provided. Malcolm will be doing a presentation. I believe that will be from 12 to 1 or 12 to 2, because we don't want to do 2 presentations. And I think that's it. Okay, cool.
All right, cool. Well, thank you. Thank you, Igor, Melissa, and ACMW for inviting me to come here and talk to you. And in trying to think about what I should talk about today, you know, I thought I could do a very detailed, low-level technical talk, but that didn't sound like much fun. I thought it would be more interesting to kind of take a step back and take a look at certain aspects of computer design throughout time. See what computers have looked like historically, what they look like today, and then just kind of play around and explore what computers might look like tomorrow. So this is computer architecture through the looking glass. So everything that I'm talking about today is on my website, songlinesystems.com. It's in development. I'm trying to update it, so stuff is kind of scrambled around. You might have to hunt for things, but everything should be somewhere on there. And everything I do is always open source, so source code, API, libraries, things like that are there to freely use however you like. So let's start with computer architecture. So this is Charles Babbage's analytical engine from 1837. This is the follow-on to the difference engine. And this was a general-purpose programmable machine. You programmed it by punching holes in cards. There's a little card reader up here. And by positioning 10 holes, you could tell it to do different instructions. And of course, the first programmer was Ada Lovelace. She wrote the programs for this, which is why you can buy glasses with her image on it and some of her work. She wrote programs for things like generating Bernoulli numbers. So this was a general-purpose programmable machine. It also had the ability to go back and reprocess cards, so you could do looping, which was pretty advanced for the time. Mechanical system, no electricity. Jump forward about a century, 1941, we get to the Zusa Z3. This is one of the first electronic programmable machines. It's an 8-bit machine, so pretty simple. Not a lot of instructions, not a lot of fancy addressing modes, but programmable. And to program this, you punched holes, but instead of punching them in cards, you punched them in recycled 35mm film strips. So it's reusing technology that was already available, and that's how you stored the program. So a few years later, 1944, the Harvard Mark I is a 24-bit machine. So you're getting a lot more sophisticated, more instructions, more addressing modes, and so on. The Manchester Baby, 1948, 32-bit machine. So pretty powerful. This was a prototype for what came after, which was the Manchester Mark I. We'll come back to that later. And this is just a piece of the Baby. The whole thing actually looked like this. So we're solidly in the realm of room-sized computers at this point. Quite an amazing undertaking. And then 1961, IBM comes out with the 7030. This was a 64-bit machine. This is the first of what we would eventually call supercomputers. It was also nicknamed Stretch for, sort of obvious reasons. 64-bit. So this had all kinds of sophisticated addressing modes, lots of powerful individual instructions, lots of advanced architectural mechanisms for speed, and so on. So we see this trend of increasing complexity, increasing number of instructions that can be used on the machine, and so on. And that trend continued throughout the 60s and into the 70s. But around this time, a couple of other interesting things happened. One was 1962. John F. Kennedy gave a speech where he announced to the world that we were going to go to the moon. And we're going to land someone there and then bring them back safely. And he added, we choose to do these things not because they're easy, but because they are hard, right? This is why you do a capstone in your senior year. This is why you did an SLP, Service Learning Project at Clark. Because when you undertake very difficult tasks, you solve problems along the way. Those have their own benefits. So one of the really hard problems that NASA had is how do you fit a computer on board a spacecraft? Because, a spacecraft, it was barely big enough to hold 2 people, and computers look like this, right? Or like this. You don't want to try to cram that inside a little tin can. So the other thing that had happened around this time was 1958. Jack Kilby invented this, first integrated circuit. And it was about 1 inch long, had a couple of transistors, a few other components, some wires. Not terribly impressive by today's standards, but it was the first time anybody had built an entire circuit on one substrate. And NASA made the bold decision that they were going to build the Apollo guidance system out of integrated circuits. So they contracted MIT's Lincoln Laboratory to start building ICs, and they only built one type of IC, that was a NOR gate. And they designed the entire computer out of NOR gates. They became the biggest consumer of ICs on the planet. They were buying more than 50% of all the ICs being made. And of course, the Apollo mission was fabulously successful, and this helped propel integrated circuits forward in their development. So throughout the 60s, ICs got smaller, we could put more transistors on them, they were more reliable, easier to manufacture, and that continued through the decade until about 10 years after the start of the Apollo mission. Intel came out with their 4004 processor. Going the wrong way here. So the Intel 4004, 1971, single chip microcomputer. Never been done before. And they basically took, a big part of those room-sized computers and shrunk it down into this tiny little chip, also about 1 inch across. Very, very simple, 45 instructions. Not a whole lot, but enough to do all the things that you wanted to do with a general purpose computer. 3 years later, Intel came out with the 8080, which was an 8-bit processor, and that launched a whole generation of homebrew hobbyists. 244 instructions, so 8 bits, how many opcodes can you fit? How many different instructions if you got 8 bits to specify? 2 to the 8, 256. So they used 244 of those. They had a few opcodes that weren't used, so they were redundant. Zilog 1976 came out with their Z80. This is my all-time favorite microprocessor. It was such a blast to work with. It had 500 plus instructions in it. And it was backwards compatible with the 8080. It would run 8080 code. So they took a few of those unused opcodes and they repurposed them. And said, if you see this opcode, it's a prefix. Look for the next byte, that'll tell you what to do. So they had hundreds of instructions in here, and they were powerful. You could use one instruction that would say, let's take this many bytes from this location in memory, copy them over to here one byte at a time. One instruction. It's really fun to program. So then Intel came out with their 8086, also the 8088. They were similar to each other, which eventually went into the first IBM PCs. Motorola made their 68000, which went into the first Macintosh. And these were incredibly powerful machines, thousands of instructions. So these are solidly what we would call complex instruction set computers, or CISC machines. These had gotten so complex that the engineers could no longer build hardware to execute the instruction set. Because you would have all these different addressing modes and all these multiple things you wanted to do, checking conditions. And if you think about how hard it is to design hardware for like a traffic light, try to imagine coding thousands of instructions, right, in hardware. They could not do it. So they started using something called microcode. And the idea of microcode is inside your CPU, you build a really, really small, simple, fast computer. And that computer runs programs within something called microcode, and those programs interpret the machine language. So when you have an instruction that says copy memory from here to there, it's not a set of hardware that's been built as a state machine or something. It's just a little program running step by step, saying, okay, first take this, copy it over there, increment this, compare it to that, and so on and so forth. So in this picture of the 68000, these two blocks, that's just code. That's the microcode and the nanocode that's driving a processor inside here. So you got a little computer inside a big computer. So people went crazy with this. Everybody wanted to have the biggest, baddest processor with the most instructions, the most features, and people just started microcoding everything. And we got these incredibly complex machines that did all these amazing things, but they did not scale well. And performance started to degrade. And so as people were making more and more complex instruction sets throughout the 70s, a counter movement started, which was, let's make a reduced instruction set. And so in particular, David Patterson at UC Berkeley started the Berkeley RISC project, and a couple of years later, John Hennessy, Stanford MIPS. And these were theoretical models, but there were also some actual implementations of them. There were a few commercial instances. And so people got interested in this idea of reducing the instruction set. So going back from the thousands of instructions to something with very few instructions that would run really fast. And the real commercial breakthrough came in '86 when the first ARM processor appeared. So how many people here have heard of ARM? Right, a few years back, not very popular. It's getting more mainstream now. But it's been a powerhouse in the computing industry. If you look at number of units shipped, Intel ships, 50, 100 million units a year. AMD maybe a tenth of that. Apple a few million. 2023, ARM shipped 30 billion units. Right? This is what's running our planet right now. ARM processors are in smartphones, they're in tablets, they're in your smartwatch, they're in Raspberry Pi is ARM-based, they're in routers, they're in gaming consoles, they're everywhere. And they dwarf the processors that we're using in our laptops and desktops. GPUs, of course, are taking over now because of AI. But this reduced instruction set idea has really been the dominant type of processor running for some time now. And if you came from Clark, you might have your favorite or most dreaded processor. Pick 18F1220, everybody remember that? Right, so 76 instructions. It's a little chip, 18 pins, costs a few bucks. Only 76 instructions, but you can do a lot with it. And PIC also makes a 16F line with 35 instructions, and there's an older PIC 10 with 33 instructions. So, you could fit it almost in 5 bits. So, the white rabbit we are following now is the question of what's the fewest number of instructions that we need to make a useful computer. We know we can get away with 33. We know we can use thousands of instructions if we want, but we can get down to, 30-some. How low can we go? So let's go down the rabbit hole and explore this. So, question, could we make a machine with a 4-bit instruction register with only 16 instructions? And I'm going to say the answer is yes, and I've laid out some of the instructions we might use. Add, subtract, unconditional and conditional branch, a move instruction, a few logic operations and or not, a shift, input, output, call, return, and we've got a few extras left over that we could put in. So yeah, we can definitely get away with 16 instructions. What about 8 instructions? Could we make a machine with a 3-bit instruction register? And if we don't mind doing some work, yeah, I think we can. For example, we could get rid of the subtract, because you can just add a 2's complement to do subtraction. We could just do a conditional branch, and if you want to branch unconditionally, turn on your 0-bit, right? We've got the move. We only need a NAND, because we can get all other logic operations out of a NAND. Call and return, and then we can memory map the I/O and more sophisticated functions, so we just move to certain locations. We can get away with that. What about 2 bits with 4 instructions? What about 1 bit with 2 instructions? Can we build a machine with only 2 instructions? What about 0 bits? So 0 bits doesn't mean no instructions, it means 2 to the 0 instructions, that's 1 instruction. But if there's only 1 instruction, how many bits do you need to specify? You don't need any. So what should I do? I'm doing the same thing I always do. So can we make a computer with 0-bit instruction register? Yes, we can. And so I'm just going to call this the 0-bit computer, or the ZBC. And it's a pretty basic architecture. Our 1 instruction is going to be move. So we're just going to say move from here to there, move from here to there, move from here to there. And since we know the instruction is move, we don't have to actually say move. We just have to say here, there, here, there, here, there. Just list the operands. Where should we move from and to, from and to? All of the I/O is going to be memory mapped. The ALU, any other special functions we want, are going to be memory mapped. The program counter is going to be memory mapped. I'll just store it at a magic location, like 65535, and whatever value is in there, that's the address of the next instruction to execute, which isn't an instruction, it's just a pair of source and destinations. So this is a little goofy, but it's pretty easy to simulate. So if we write a C program to simulate it, this is our entire main loop, right? Take the program counter, read what's in memory there, store that in from, increment it, read what's at that location, store it in to, increment it, and then read from the memory from the from address and write to the to address. Just do that forever. So that's a little goofy, but it's not too hard to do. And so this is a complete emulator for the 0-bit machine. It's about 2 pages of C code. And a lot of it is just startup, processing arguments and such. This is the main loop that we just looked at. And the rest of this is just the reading and writing from memory to map certain magic addresses. So if I write to location 1000, that's a display port, and it'll display whatever value I wrote on my screen. If I wrote to 1010, that defines the function the ALU should do. 10, 11, and 12 are the 2 inputs to the ALU. And if I read from 1013, that's the output. So I'm just memory mapping the hardware into different locations. And it's tricky to program, but you can do it. So for example, here's a counter. This should just count from 10 to 0. And the way I define this program, it's a memory address and a value, memory address and value, memory address and value, and if you don't put a memory address, it just goes in the next location. So all of these are just stored sequentially in locations. And so the program basically says copy from location 512 to 500. Well, 512, I got the number 10 stored. 500, that's where I'm storing X. So this does X equals 10, and so on. So doing branching, you have to load a value into 65535, that's the program counter. And conditional branching, you can change what address you want to store something in. It gets a little funky, but it's not too hard to do. And if I run this, there's my counter. It counts from 10 down to 0. And then it's not a real computer until you've generated primes on it. So here's my prime number program, 157 lines. And I've added some comments to remind me where the certain memory map locations are. Here's the ALU is for comparing. Here's my variables. There's the display output and so on. And it's basically just, you know, repeatedly trying possible factors for consecutive odd numbers. And if I get above the square root and haven't found a factor, I call it prime. And if I run this, it pretty efficiently generates prime numbers. And if we look at the beginning of it, we can see we've got 3, 5, 7, 11, 13, and so on. So yeah, we can definitely program this 0-bit machine. It's not terribly easy. It's actually pretty fun, but it's tricky but doable. So, and this is computationally complete. Anything you can do in Java, C, Python, should be able to do on the 0-bit computer. So let's explore this. And I love this quote from William Blake. Art is the tree of life, science is the tree of death. Now this is not a diss on science. It's not saying science is bad or you die if you do science. It's talking about, to me, the idea that art is a creative process. When you do art, you're taking something that doesn't exist yet and you're bringing it into existence. You're putting things together and making something new. Science is the opposite process. Science, you're taking something that's there and you're breaking it down, putting it into smaller and smaller pieces and studying those and breaking it down. You don't want your science to be creative, right? As a scientist, you have to be creative in how you think about things, but science itself, you're not trying to create something that's not there. That's a disaster, right? You're trying to understand what is there, and that's sort of more the feeling of death, and creation is more the feeling of life. Both essential, both linked into each other. You got to have one to have the other. So I want to go forward with the mindset of an artist here. And I want to start creating, instead of studying what's already out there, I want to start exploring what we might do that isn't already done. So basically we're going to take advantage of the simplicity of a 0-bit computer. It's a really simple architecture. There's not a lot of requirements on it. This lets us play around with our definitions, push the boundaries of what we think a computer has to be, and we're going to see what we can come up with. So we're going to start with the address space. So most computers today, if you look at the memory addresses, they're just integers, 0, 1, 2, 3, 4, 5. If you look at a PIC processor and the program memory, the addresses are 0, 2, 4, 6, 8. They're always even numbers. But they're still basically just sequential integers, maybe going by 2s or 4s or by 1s. That's what we've got today. That's pretty much every von Neumann machine. So what would happen if we were to address our memory using rational numbers, using fractions? So we have an instruction at location 1/2 that says increment register at memory location 2/3, right? And that feels a little goofy, but in reality, it's really not different from using integers. Because integers and rationals, the technical term we use, is they have the same cardinality, right? We can map from one to the other. So this can be thought of as just kind of renaming the integers. So it looks goofy, but it doesn't really get us into a different kind of space. But what if we use real numbers for our memory addresses? Now we got something interesting going. So this is our first major tweak. We're going to make the space continuous. And our memory is going to take on addresses between 0 and, we're not going to go to infinity, but 0 and 1, 0 and 40, some number. And so you've got, this infinite number of addresses in this little region. Okay, so we got continuous space. Well, as soon as we do that, we've made a problem for ourselves. And the problem is related to this business of the program counter. It's called a program counter because it counts. First instruction, next instruction, next instruction, right? Those addresses in our traditional computer are countable. Z is countable, R is not. There's no way we can make a program counter started at 0 and then increment it by some amount to eventually get to every instruction. That's what it means when we say R is not countable. It's bigger than Alice not. So we got a problem with the program counter. How do we deal with that? We're going to get rid of the program counter. Toss it out. All right. We got continuous space. We got no program counter. Next question. How do we know what the heck we're supposed to execute? Because the program counter tells you, hey, do this instruction next. We just tossed it out. So how do we know what to execute? We'll just execute everything. So instead of going step by step by step, we're going to let everything execute all at the same time, constantly. So there's no more stepping from one instruction to the next. So now we've made time continuous. So we got continuous space and continuous time. All right, getting a little weird? Mm-hmm. All right, let's see what else is in our rabbit hole. Anybody recognize this?
Chili peppers.
It's a chili pepper. Specifically, it's a ghost pepper. So peppers are rated on the Scoville scale, and a typical hot pepper is several thousand SHU. Ghost peppers break 1 million. Unbelievably hot. And every now and then you'll find a story of someone who decides to try to eat one of these, and they usually end up in the emergency room. So this is a really hot pepper. So why are peppers hot? Why do they create that burning sensation in your mouth? Well, it's pretty simple. There's a chemical called capsaicin. And peppers contain this chemical, and when it's released in your mouth, it bonds with pain receptors. And a little bit gives you a flavor, a little bit more gives you a warmth, a little bit more gives you heat, a little bit more gives you pain. And the more capsaicin, the more pain. Now, you can extract this chemical from peppers, concentrate it, put it in an aerosol form, and you get pepper spray. And if you make it even more concentrated, you get something called bear spray. And bear spray is a high enough concentration of this that it can deter an attacking bear. Don't try this, but you can buy this stuff. So if you happen to run into one of these, right, pepper spray can be a powerful deterrent. But if you bump into these two, that's a totally different story, because pepper spray will not affect birds. And it's not that these two are so tough they can withstand the intense pain of pepper spray. It's that birds don't have receptors for capsaicin. And so it's nothing to see a bird sitting in a pepper bush just happily chomping away on what I guess tastes like peppers. It doesn't generate any heat, doesn't generate any pain. So when we see a chili pepper and we think it's hot, there's something not quite right about our understanding of chili peppers. Because if we got into a debate with this bird, it would say, what are you talking about? All right, let's look at something else. What happens when you kick a ball? You put one foot down on the ground, you bring your other foot back, maybe you're running to get some extra speed, you bring your leg forward, the foot hits the ball flies, hopefully makes a goal or whatever you're trying to do. Pretty simple equation, right? Except a few hundred years ago, a guy named Newton told us it's really not that simple. Because when you kick the ball, at exactly that same moment, the ball is kicking you. And we don't think of it that way, right? Because we weigh more, we've got a foot on the ground, we've got more friction, and so on, so we don't even necessarily notice. But guaranteed, however much force I'm hitting that ball with, it's hitting my foot with the same amount of force. So what we're talking about here is subject and object. And if I say I kick the ball, I would be the subject, the ball would be the object. And the point here is that we as humans ascribe special significance to the subject. We think that since I'm the one initiating the action, that the ball is the receiver of that action, and that's the end of the story. And we miss this other part, that there's actually a way in which the ball is the subject and I'm an object. When I say I taste the pepper, I'm the subject, pepper is the object. And I taste it because, when I bite into it, the chemicals in the pepper react with the chemicals in my mouth. But at the same time, the chemicals in my mouth are reacting with the chemicals in the pepper. And so in some sense, the pepper is also having a similar experience. And we understand this dichotomy between subject and object. We even have terminology for it. For example, suppose you're going to a swimming pool and you ask someone, what's the water like? Well, they might give you an answer like it's nice, or it's cold, or it's perfect. Or they might give you an answer like it's 72 degrees, pH is 7.5, and it's 2 parts per million free chlorine. And we have terminology for describing these two types of answers. We call the first one subjective, the second one objective. And this is literally the answer from the point of view of the object, the water. This is the answer from the point of view of the subject, the person going into the water. But if you really want to know what the water is like, this is the true answer. That's describing the water. That's not about the water. That's about how I like my swimming pool to be. That's about what I'm wearing. But we ascribe special significance to this subjective view because that's we, that's I, that's me. That's where the person doing the analysis is, right? So another term for this is ego. And it's not ego like I'm the best football player the school ever had. It's ego as in confusing our identity with our thoughts. And if you ever get to read some Eckhart Tolle, I highly recommend anything by them. Some really good writing. I love this last sentence. Ego is there in the absence of a witnessing presence. So a witnessing presence to me means that you're in some situation and you're just observing. You're not judging, you're not categorizing, you're not labeling, you're not processing or analyzing, you're just witnessing. It's a really hard thing to do because we have this sense of ego. Okay, so what does this have to do with computer architecture? So there's a notion of dualism. Dualism is the tendency to break the world into subject and object, sort of splitting things into two different categories and thinking that there's some fundamental difference between them. And some of the earliest electronic computers were built with a very dualistic view of computation, which is not surprising. That's how we sort of interact with the world. So if you look at the ENIAC, it did not have software. It was programmable, but it didn't have software. The program was actually this combination of cables and knobs, and here these people who are programming the computer are moving cables from one spot to another, changing the knob setting. They're manipulating the physical stuff. That's how you programmed this machine. And so the code would act on the data, would modify the data. There's no way the data could come back and modify the code. You can't increment a register and when it hits some point, suddenly one of these cables flies out and plugs into somewhere else. So it's a very one-directional interaction. The code is the subject, the data is the object, and it doesn't go back the other way. The data does not affect the code. And that's sort of counter to this idea of a non-dualism. So while the ENIAC was being built, the designers realized, hey, we had an opportunity. We should have made the program soft. We should have put it in memory so we could change it. And so the Manchester Mark I, which came right after the Baby, that was one of the first stored program computers, where the program was actually stored electronically so that you could modify it. And so the software could come back and actually change the program. You could have self-modifying code. And this is ubiquitous today. All of our computers have this ability to self-modify, and it's actually necessary for most of what we do with a computer. Think about what happens when you click on an icon and you want to run a program. That program is data sitting on your hard drive. And a program, which is part of your operating system, loads that data, copies it into memory, sets some other things up, and then suddenly changes the program counter to start executing that data as if it were code. And your computer, which was previously running instructions to do this copying, is now doing this other stuff instead. So we depend on this ability for most things that we do. And one consequence of this is if you look in memory, if you've done debugging, you've probably had this experience. If you just look in memory and you look at some memory location, you find, say this 32-bit value, is it data or is it code? You really can't tell. It could be, you know, part or all of an instruction or multiple instructions. It could be a big integer, it could be a floating point number, it could be part of a JPEG image. You can't tell just from looking at it whether it's data or code. But you can get some hints sometimes by looking at the program counter. So if the program counter is pointing to something, it's probably code. If it's not, you're probably going to say fault or crash. But if the program counter is pointing, it's probably code. If it's an operand to an instruction that you know is code, then it's probably data. But we still have a dualism between code and data. At any given moment, we can identify this is the operand. It says what to do. Sorry, this is the operator. It says what to do. This is the operand. That's what's being done to. That's the thing that's being incremented. This is the thing that says increment. We still have this distinction between code and data. But the PC will help us figure out which is which. Well, remember, we got rid of the program counter. Oops. So how do we know what's code and what's data? We can't tell the difference. But we actually don't need to. And so we're going to make the system completely egoless, which means there's no distinction between something that's performing an action and something that's having an action performed on it. So complete, perfect non-dualism across the entire system. All right, so we've got an egoless continuous space-time system. And at this point, we're starting to see some alignment with natural processes. We've got spatial continuity, temporal continuity, non-dualism. These are things that we sort of can observe in the world around us. And so we can push that and say, what else could we take from nature or from the universe and add to our system? And I want to add one more thing, and that's non-locality. And the idea of non-locality is that when there's some action and you look at the effect, it's usually not an isolated effect, because effects will be causes for other effects. So for example, if you strike a match, what happens? Well, it bursts into flame at the end. But that's not the whole story. Smoke comes off, right? Particles leave the end of the match and begin to float up in the air. And those particles might eventually hit a smoke sensor, which opens up a water valve and floods the building with water, right? Very remote, non-local effect. This also creates heat. The heat warms the air around the head of the match. That difference in air temperature causes currents. And you get a breeze, and maybe that breeze knocks over a piece of dust, and maybe there was a dust mite on that piece of dust, and now it's laying on its back. And while it's looking at the ceiling, it has some amazing insight that a million years from now changes the fate of the universe. So you've probably heard of the butterfly effect. That's what we're talking about here. A butterfly flaps its wings twice instead of once, and a week later you got a tornado on the other side of the planet. And it's because anytime there's an action and there's a result of that, it's usually not isolated. It's going to cause other things to happen, and those can cause other things to happen, and so on. So there's two principles here. One is this idea of a chain of events. But then, of course, if this chain goes on long enough, eventually that'll come back and affect me. And so the word for this is karma. And there's a Western notion of karma that's like, if you step on a bug, then an elephant will escape from the zoo and step on you. And that's not the version I'm talking about here, right? I'm talking about the idea that effects are not localized. They're distributed, but yes, they will eventually come back and affect you, potentially. So, how are we going to put karma into the system? So move is our one instruction, and our instructions will be something like, move 1, 2, so copy from location 1 to location 2. Karma will mean that when we do that, we're actually going to move from a small region around 1 to a small region around 2. And the further we are from 1, the less of that effect is going to happen. So we're going to do less of a move somehow. And if we get very far away, we won't be doing any move at all. So we'll try to distribute the effects of these one instructions that we just keep executing. So this gives us an egoless, extended effect, continuous space-time system, which we call e-exist. All right, so we want to dig into this and see what this system looks like. There's a book that you can download from the website. It's a PDF. You can also get a copy on Amazon if you want a hard copy, but it's color, so lot of what we're talking about here is in this PDF that you can download, the experiment and some of the details and so on. And there's also GitLab repos with all of the original code and things like that. So the way that we're going to model this is using chemicals. We're going to picture that there's two different types of chemicals, red and blue, which I'll call source and destination. And our spatial domain from 0 out to some value will be along the x-axis. And at each point, there's just a certain amount of source and a certain amount of destination chemicals. And these code transfer instructions. So at this point, if the amount of source is 2.1 and the amount of dest is 1.7, right there is an instruction which says copy from location 2.1 to 1.7, do a move. And so, you know, we have all of these addresses, we have all of these move instructions. And I don't know how to build this physically, but you can imagine, you know, some kind of substrate that contains liquid with a different amount along the x-axis, and there's some way to pick up what the levels are. Implementation is for others to figure out. To simulate this, though, we're going to discretize, and that's sad because we want continuous space, continuous time, but we're working with, you know, discrete von Neumann architectures. So we're going to discretize space. We're going to think of a little delta x, and at each location, we're just going to picture like a cylinder that has two chemicals in it, a certain amount of source, a certain amount of destination. And then those chemical levels specify a transfer. So for example, this tube right here at location 5 has 2 source chemicals and 10 destination. That's an instruction which says move some chemicals from location 2 to location 10. So when we step forward in time, and yeah, we're discretizing time, we get a little less chemical at 2 and a little more at 10. And these other instructions are no ops. This says copy from 8 to 9, but there's no chemicals at 8 and 9, so nothing happens. But we've got, you know, some chemicals in there, and they're specifying transfers. So karma, we just blur out the effect of these transfers. If karma is 0, it works exactly like I just described. If karma or kappa is 1, if we say transfer from location 2, it'll actually transfer from location 1 to location 3. That whole range, chemicals will get moved. But most of the chemicals will come from location 2. A little less when we get further away. When we get more than a distance of 1, there's no more transfer. And the bigger kappa it is, the more that distribution. If we were to set kappa to infinity, any move instruction moves everything from everywhere to everywhere. That's madness. So I finally learned Jupyter Notebook this summer and ported all of this stuff to Python and made some demos. And so I saved these as HTML files so we wouldn't have to sit here and wait for the Jupyter code to run. But you can go through these. There's a link to the book's PDF. But basically, there's some classes in Python. There's an eExist class. We can construct an instance. We can set the karma to 0. We can display the system, and you know, by default, there's no chemicals anywhere, so it just looks blank. I can initialize some chemicals. So here I'm setting the range from 0 to 30 with 5 source, and I'm also setting that range with 5 destination. And when I display, I've got this. So a little bit of source, a little bit of destination. And these instructions all say transfer from 5 to 5. So it's not going to do anything noticeable because we're just moving chemicals from one location right back to itself. So if we step that, nothing happens. Now, if I add another instruction over here with 10 source, 20 destination, that says let's transfer from location 10 to 20. So this instruction right here at 35 should be saying let's transfer from location 10 to location 20. And if I run that, it's really hard to see, but there's a little blip right here where a little bit of chemical got transferred. There should be a little dip there, but it doesn't show up on the resolution. So let's run this, but observe what it does across time. And I'm going to step this 20 time steps. And if we do that, we can see chemicals are dropping out of here, and they're being transferred over to there. Now, that's fun for a few seconds, but then it's just kind of the same. So if I put in more instructions, so now I have a whole range of instructions from here to here that are all saying transfer from 10 to 20. And if I run that, I get a slightly more dramatic movement of chemicals like that until there's no chemicals left at 10, and then the transfer stops. All right, so if we put karma in, exactly the same setup, but here's a karma of 1. And now we get a little more distributed transfer from source to destination. And I can increase karma. Here's 2.5. And it looks like it's both speeding up and also increasing the range over which this transfer has an effect. And then here's a karma of 7.5, which is fairly high. And we're getting this kind of thing. Now, if I bump karma up far enough, eventually I'm going to start modifying these chemicals over here. And then we got a self-modifying system. But I don't have to do that. I'll put karma at 5, but instead of setting up these initial chemicals to just be 5 and 5, which are no ops, I'm just going to load a slightly different instruction. I'm going to set these initial values to say, hey, let's transfer from location 10 to location 20. And if I run that, we get something very different. It's basically one instruction repeated across, move from 10 to 20, but it's pretty hard looking at this to sort of reverse engineer that and say, oh, that makes perfect sense. So this is what we typically get when we run this system. All right, so let's talk about some experiments. This is the last part of the talk. Experiments we can run on this. So the system is very hard to program explicitly. So I took a shot at writing some equations to describe the chemical levels across time. This is for a 2-dimensional version of the system, by the way. So there's x, y coordinates. Pretty easy to write the triple integrals for these chemical levels. Pretty hard to do anything with them, except, put them on a slide. And really, really, really difficult to imagine reverse engineering them. To say, I want the chemical levels to change in this way, how should I set this up? So programming explicitly, I got no idea how to do it. I've tried a few different things, but I found something that saved me from having to program it, and that's just training it. So it works pretty well with a kinetic algorithm. So GA, basically, the idea is you're trying to get some behavior out of a system. Take a large number of copies of that system and randomize them. And see how well they do at whatever your task is. And they're random, they're not going to do your task very well at all. If I want to build an adder and I just take a bunch of random parts and throw them together, probably not going to do anything. But a few of them, just through random chance, will do something. They may respond to your input in some way, whereas most of your systems ignore your input. So take the individuals that do best, no matter how bad that is, and combine them somehow, mate them. Combine their characteristics to get a new individual. Get rid of the ones who are doing the worst, keep the ones that are doing the best and their offspring, toss in some random mutation and repeat. And just keep doing this over and over and over again. This goes back to the 60s. People started playing with GAs. And in this case, on the system, genetic algorithms seem to work really well. You can get some interesting behavior out of these with absolutely no idea why it's working. Which is always fun. So we need a gene. We need some way to modify some aspect of an e-exist instance. And we could do it with chemical levels, but that's pretty volatile. So totally out of the blue, I just came up with this idea of a bias gradient. So basically at each point x, y, I have some offset for source and destination. And if this instruction says transfer from 10 to 20, but I have a bias of 5 in source, instead of reading from 10, it'll read from 15. And there's a bias for the destination, and that gets added to the actual destination chemical level. So it's a skewing, an offset of what each instruction is actually going to do versus what it's saying it's supposed to do based on the chemical levels. And so I decided this would be my gene, and I would break my space into 8 or 10 or 20 regions, and just make a linear gradient across each region. And that would be my bias. So for mating, we can either average the bias values between the two parents, or we can go across and randomly pick a bias from one parent or the other, closer to what biology does. So that's the gene. So did some experiments on this. And the idea was basically, we want an exist system with, supposed to do a 2-input XOR. So we have 2 input regions, here and here, and we have an output region between 25 and 30. And if we want to load a value of true into the first input, we set a lot of source and a little destination. If we want false, we do a little source and a lot of destination. Everything else just has, you know, the standard 5-5 base level of chemicals. And then we're going to step this a certain number of times. I went for 50 steps. And at the end, we see how much chemical is in this output region. And if it's more than a certain threshold, we say it's true, and if it's less, it's false. And with a random individual, we can do this and see, does it actually do an XOR function? Well, probably not. But you know, if you have a function that always says false, 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 it's right 50% of the time. Because half of your XOR truth table is true, half is false. So we can get some sort of behavior. So there's all kinds of tools. You can look at the READMEs later and such that explain this. But basically, you can make an exist instance. I can make a load function which sets the source and destination levels in those output regions based on whether I want them to be true or false. Here's some code that will go through all the possible conditions. So all combinations of true and false with 2 inputs A, B. Clear the system. Set some base chemicals, load in the input chemical levels, step 50 times, calculate what the correct answer should be, look at the output range, see how much chemical is in there, decide what the system is saying the answer is, and compare that. And then tally up the score based on that, and that's the individual's fitness. So I ran this a lot of times, and here's the scores that it came up with, right? 50% probably was just always saying false. We got a 58% right off the bat. I got a 26%, which did really badly. But that's hard to do. You've got to be wrong 3 times out of 4, which takes some skill. And so I ran this a whole bunch of times because I went away and came back later. It actually got some pretty good performance pretty quickly. Generation 19, it had a best score of 72.5%. And if we look at the actual values, this should be false, true, true, false. Well, that's definitely false. The total output of 4, output of 32 is true, 19 is true, 15. Well, that's pretty high. But if we were to divide the output range, you know, between 16 and 19, it's doing an XOR, but it's kind of not really. This is what the genome looked like for that. So those sporadic lines, those are mutations. And throwing in mutations seems to be essential. This individual was doing much better. The 2 false outputs, 7 and 8. The true outputs, 22 and 29. And so let's just look at a couple of these. So this is putting in false and false. So the XOR, the output should be false. So we step it 50 times, and some chemicals appear in the output, but most of the output region stays pretty close to 0. So that's a solid false on the output, which is correct. And in this case, we're putting in false and true. So the XOR should be true, so we should see chemicals in the output. And yeah, pretty quickly, lots of chemicals go into the output region. It's telling us the XOR output is true, which is correct. So this was a good evolution of a 2-input OR gate, XOR gate. We can do a NAND gate also. I'll skip over that one. 3-input XOR took some time. This I had to run for a few hundred generations. But eventually it did what it was supposed to do. So here's a true, false, false. So the XOR should be true. And if we step that, yeah, we get lots of chemicals in the output. So that's doing the right thing. And this one is true, true, false, and we should get very little chemicals in the output. This is hard, right? We've got lots of this stuff over here lots of transfers happening, but the output reagent mostly stays pretty low chemical, but ends up reading as a solid false. So we can evolve simple logic gates, which, you know, is not that exciting in itself, but it was surprising to me that this could actually do anything useful, anything like, you know, deliberate, because it's such a random seeming system, right? So I tackled tic-tac-toe. Thought it would be fun to see if it could learn to play tic-tac-toe. And basically I set up a way for it to just play a whole bunch of games of tic-tac-toe. And again, random population of individuals, and they would just make moves based on what the board looked like at any given moment. No reason that this should eventually learn how to win at tic-tac-toe, but it did. And if you let it go first, it would win almost every time. So that was kind of cool. So then I tried a lunar lander, made a little video game where you have a spacecraft and you control the amount of fuel being burned, the amount of thrust, which slows its descent, but if you run out of fuel, you crash. And with different initial conditions, tried to get it to where it could always land softly on the surface of the moon, and it was eventually able to do that every time. And then I had a student who, for their service learning project, was interested in this, and so he took a driving game and tried to hook it up to eExist. He ported it to CUDA so he could run it on his GPUs in his graphics card, and he got some reasonably successful driving. Sometimes it would go off the road, but he had some successes with that. And then I switched to the two-dimensional version of eExist and started processing images, and got some databases with different poses of a set of 6 individuals and see if it could recognize the differences. And it did this almost immediately. It was able to get perfect differentiation after just a few iterations of the algorithm, which was surprising and freaky. So this was deep in the heart of COVID at this point, and lots of spare time. And so I woke up one day and thought, how about brainwave interpretation? So I had a little brain scanner I got from Amazon. It would record alpha and theta waves and so on, and I put that on and recorded listening to Bach for 5 minutes, solving integrals for 5 minutes, and then watching SpongeBob for 5 minutes. And I figured those are probably about as different from each other to see if it could differentiate, and it did not work. But it wasn't terribly scientific. I still think there might be a way to do this, which would be interesting. And then I woke up one morning, again, during COVID, and had this horrifying thought that, like, you know, what if none of this is real? What if this is all just a big simulation? So I set it to work on picking winning lottery numbers. And, you know, I went to Powerball's site, and I pulled down the winning lottery numbers for the past year, and fed those in, and trained the system for a while, and then let it pick what the next winning numbers would be, and bought a ticket for that. And fortunately, that did not work. And it's fortunate, because if it worked, I'd have money, but what would I do with it? Because all this would be fake. It would be a simulation, and, you know, food doesn't taste as good that way. So this is the last project I want to talk about, last experiment, this idea of a virtual ecosystem. This was another former student service learning project. They wanted to build a little ecosystem on their computer and model it. And that had gotten stuck in my brain when I saw it. So a few years later, I did this, and the idea was, let's make a population of individuals, each one of these controlled by its own copy of eExist. And these individuals can move forward, or they can turn left or right. Each time they move, they use energy. When they hit a little green square, that's a piece of food, they gain energy. They can attack another organism, so if you come up to the side of a creature, you can drain energy from it, as long as you sit there. They can also mate if they come face to face and have enough energy, and they create an offspring that's a combination of their genomes. And the survival metric is simply survival. Just let these things run around, and as long as they're able to move and they have energy, they're alive. They can keep moving, reproducing, and so on and so forth. So basic setup like that. And when I first made this, they would move around for a while, and then they would just stop. Everybody found a happy spot, and that was all that ever happened. So I added a daylight cycle where all artificial light level would raise and lower across time. And these energies, these creatures get a really simple input from around them. They just know if there's something there or not. They don't know what it is. They don't know if it's food or another creature, which way it's facing. It's just something there or it's not. But they could also sense the daylight cycle. And when I put that in, they started to move around. So here I had color-coded them for another experiment, but this is what they do. They just kind of move around more or less randomly. They'll eat. When they lose energy, they get darker. When they've got a lot of energy, they're very bright. And I give them each an ID, so I can identify them. I also had a drone you could put into the system and drive, go over and interact with them and see what they do. That was kind of fun. So as I let this simulation run, and this was across days and weeks, I started to notice that there were some individuals from the earlier generations that still survived. Now, by and large, individuals die off, so these ID numbers would get bigger and bigger and bigger. But I'd occasionally find, a very small number, meaning it was, a first or second or low generation individual. This is another experiment. So I flooded the world with food to see what they would do. And, some of them just go back and forth and hope that food appears. Some of them just kind of move randomly. But this one individual up here seemed to have a habit. When food would appear, it would run around and gobble it up. And then it would sit there until more food appeared. And then it would go around and gobble it up. And it just did that over and over and over again, which seemed interesting. All right, so then I was looking at longevity after that. And so here was a graph of the IDs of individuals across time. So after 100,000 time steps of this simulation, all of these individuals, they're 100,000 time steps old. These are first-gen creatures. It's a whole bunch of them. Each square is a creature. They're all jammed together right there. So after 100,000, lots of survivors. 200,000, not as many survivors, really just this group right here. 400,000, we've got 1, 2, probably 3, 4, 5, 6 first-gen individuals. So the older creatures are starting to die off, which you would expect, right? Because it becomes harder and harder to stay alive. Out of the million cycles, we had 1 first-gen creature. A few creatures that were pretty old, so these were, 800,000 cycles old. But that population was still dying off. And at 2 million cycles, 1 pretty old individual, a few that were fairly old. Most of the population was young. So it made me wonder, is this random? Is it just there happens to be an individual who's older? Or is there something about these older individuals that's causing them to still be alive? Is there a survival advantage with getting old? So I tried an experiment. I took 25 individuals that had been trained for a period of time, and I put them into an empty world, and then I took 25 random individuals, put them into the same world, and let them just run around. That was the red-blue thing. And very quickly, the untrained individuals, they all died out. 18,000 cycles, and that was it. They were all gone. And the old individuals who had been trained, about 20% of them died. The others still alive, running out. Now, they would eventually kill each other. But this suggested there's some kind of advantage to this longevity. These creatures are actually learning something about how to survive against other organisms that these untrained individuals didn't know. So the last thing I did with these was I started to wonder about free will. And free will, is always a quagmire to get into. Do you have a choice? And I started with the idea that presumably we make decisions based on what's in our best interest, right? If you're a rational entity, you do the thing that makes the most sense for you, based on what you currently know, what the available data is and what the available processing is. And then I asked, when does this not happen? When do you act contrary to your best interest? And we really shouldn't do that, right? That's kind of a strange thing to do. So why would you go against this So for example, maybe you want to win a bet. So you're going to go out and you're going to eat a worm, right? Which is not in your best interest usually. Or maybe you just want to prove that you have free will. So you're going to walk into a random classroom and sing the national anthem in the middle of lecture, just to prove you can, right? Or maybe you just want to alleviate boredom, so you decide you're going to jump out of an airplane with a parachute. But I would argue that all of these things are still in your best interest, right? I'm not going to eat a worm unless I'm going to get enough money to make it worth my while. Unless it's got to be in my best interest. If I'm going to walk into a classroom and embarrass myself, it's because I have a point to prove, and it's that important to me to prove the point that I'll live with the embarrassment, right? So I would say that even when you seem to be doing something that goes against your free will, you're still acting in your best interest. So if all your decisions are made based on some sort of algorithm for what's the best outcome for me, what does it mean to have free will? What's the choice we can actually make? So when you look at it from that perspective, free will starts to look a little bit like randomness. And the idea I was playing with is maybe the only free choice you can make is a random one, which clearly might not be in your best interest, right? So I decided to put this into the virtual ecosystem and pick out a small set of individuals and give them free will. Give them the ability to make a random decision once in a while, not every time. They would still be driven by the e-exist model, but there was a small chance that whatever decision they were going to make, I'm going to go forward, turn left, turn right, or stay still, would be tweaked randomly. And I didn't want to use pseudo-randomness because this is a genetic algorithm, it's a learning system. Presumably it could possibly figure out the pattern of a pseudo-random generator. I wanted true randomness. So I had two sources. One was a place called Hotbits, which is in Switzerland, and they have a radioactive source and a Geiger counter. And it detects when the source emits particles, and that's a random process as far as we know. So they can use that to generate numbers. They're not in operation anymore. Random.org is, and they have some sources picking up atmospheric noise. And that's presumably a random source. Not just very hard to predict, but truly random at a quantum level. So I rewired the system, and I decided when I create an individual, if their ID ends with a 9, they're going to have free will. IDs 0 through 8, they're going to follow strictly what their programming says. But every 10th individual is going to have the opportunity to make random choices that might be something like free will. So I started with 10% having free will. And across a number of cycles, the purple line, that's the individual with free will, pretty quickly overpowered the deterministic individuals. So after about 30,000 cycles, more than 50% of the population was the ones with free will, even though they started at only 10%. And then it came back down and they crossed again, and the free will individuals were more dominant, but after 300,000 cycles, definitely more than 10%. At free will. So that made me think there's some kind of thing going on here. There's some sort of survival mechanism that they're leveraging. So I ran this for more time. This ran for, I think, a few months. And after 4.7 million cycles, the oldest individuals, none of them had free will. But here's an individual with free will. Here's one, here's one, here's one. And so some of the population, still more than 10%. Had free will. And I let it run some further. When I got out to about 6 million cycles, top 10 individuals were all the ones with free will. And across the top 20, almost all of them were the ones with free will. So there was some sort of survival advantage there. And why did this happen? I have no idea. Unfortunately, when I did this, I had not yet coded up something to capture all the details of what was happening. And I've gone back and put that in, but I haven't let my system run for months to rerun these experiments. But I've analyzed the data that I did capture, and I don't have a clue why this is happening. But it almost makes some sense, right? If there's a predator and you randomize your path to wherever you're going each day, right, it's going to be harder for that predator to know where you are. And it might be something that simple. So So that was a fun experiment, and then at this point, I kind of put this aside for a while, and I'm just now dusting it back off, putting it into Jupyter notebooks, put it into Python, that kind of thing. So this is one of a number of possible next steps. So understanding the free will work better, doing more two-dimensional work. The 2D work is really slow because the karma, in particular, if it's any significance at all, you have to do so much work to perform one move operation. Looking at different evolutionary schemes, all of that stuff with the GA, that's all the first thing I thought of. The bias gradients, the mating mechanisms, it was just the first thing I started with. And it's certainly not going to be the best, but there's a lot of work to do there. Finding other ways to program it besides the GA would be interesting. I started to work on a project where I was going to have these things create art, and I actually had a robotic arm I'd never used for anything, so I was going to let these individuals control that and draw artwork, and then take a camera and hook it up and let the rest of the population look at it, and whichever ones generated the most change in the system, those would be considered better works of art. And evolve a population of artists and see what kinds of things they came up with. Also creating a language, so letting these individuals share some aspect of their chemical levels and give them some information to convey, and see which ones are more successful at conveying different pieces of information, and see if we could let them evolve a language for communicating. Physical implementation is the ultimate goal, and I have a few ideas how to do this, but nothing very practical. And it just feels like there's tons of experiments, directions you could explore with this, way more than I'll ever get to, but I think it's a fun system to mess around with. So that's all I got. Thank you for your attention. We went hour and a quarter, but thanks for hanging in there with me. If you got any questions, I'd be happy to answer them. Yeah.
The free will thing, are you, like the idea of why the free will thing works, that you thought about, remind me of when I read about some like the older chess playing AI generator machines, and how like it can be beaten by 1-year-olds because 1-year-olds do things that they are not programmed to follow because they're expecting you to do like an optimal path.
Yeah,
but
exactly.
They have to recalculate everything and then.
Totally.
That's interesting.
Yeah, I think that's probably a big part of what's going on here. That's a really good example. Yeah.
So the computer architecture that you proposed, I may have missed this, but can you think of scenarios maybe right now or in hypothetically another world where someone would prefer this architecture over our current implementation?
I don't know what this architecture can do.
Yeah.
But my gut feeling, the way that it came about, was really kind of by trying to think about sort of what goes on in the universe, and can I move the model of what a computer is closer to that. And if I've succeeded in doing a little bit of that, I kind of feel like there's probably some advantage to that. I don't know what it is, but my gut feeling is, yeah, there's probably some way in which this might be a useful model. Although I've told people, I think when we find out what the ultimate computer is, it's going to end up being something that looks a lot like a mountain or a river or something. So, and I don't know what exactly that means, but yeah. Yeah.
Well, if you wanted to use the let's say, you still lose energy.
I don't know. I mean, losing energy over time would make sense. That would be pretty straightforward to implement. I don't know why I went with a daylight cycle. I was bored. I was just kind of like spitballing things, and that's what I went with. But yeah, slowly losing energy would make more sense because that's what actually happens. And yeah, that would propel the movement. I think I was afraid they would die too quickly. Yeah.
Was it, because you mentioned that the image recognition was very, worked very well on that? Are you planning on working on more experience for that one?
I don't know. So that was a two-dimensional version, and like I say, the 2D version is really slow. So the experiments were so slow that by the time I finished an experiment, I had like 20 new experiments I wanted to try, and I quickly, overwhelmed my mental stack with things to explore. So if I find a faster way to do the simulation, would be interesting. Yeah, I don't know exactly how they responded to it, I just noticed that they moved around a lot more, that cycle there. But,
Like I assumed that they have some kind of circadian disease.
yeah, that would be interesting to see if that developed eventually, because if there's a survival advantage to that, theoretically, the system would eventually choose creatures of that. That would be interesting.
They'll be way more complex on its own, so that way, you can see which creatures are the longest, either the ones that scripted circadian rhythms or ones that don't follow that.
Yeah, totally. Part of the challenge with that was I had not made it restartable. I didn't expect to be running these things for months at a time. So when my computer would crash, I'd like have to start over. And it's not hard to checkpoint yourself along the way. By that point, I would have had to go back into the code that I'd forgotten and add that in. So as I'm dusting it off over this past summer and now, that's one thing I want to put back in there is checkpointing, so we can let it run for a few years, come back, see what it's got.
What were some of your ideas for physical implementation? Because you mentioned you had a few.
So I thought maybe I could use charge instead of a chemical level, and have some kind of steering network, collection of controllable switches, and then when, it's all about transfer basically. So if there was a way to connect the charge on this capacitor to the charge on that capacitor and sort of bleed off some of that might get me there, but that's a hard thing to do without totally discretizing everything and really just kind of ending up with simulation. Putting it on an FPGA where I could do all of these transfers truly in parallel would be nice. And it's a pretty good approximation of parallelizing because I calculate all the transfers first and then I do them all at once. So they are happening at the same time, but it's, stepwise. So, trying to make a Verilog version of this and then get some parallelism is probably the next thing I'm going to try for speed. Yeah.
Are you able to utilize, because it seems very similar to a lot of machine learning stuff, and that commonly uses GPUs for speed and parallelism. Have you been able to utilize GPUs for this at all, or is it mostly just?
So Caleb, the student who did this for the SLP, he ported this to run on GPUs and got some speed up, but it didn't scale for some reason, I guess because we didn't have enough GPUs. I tried porting it from Java to C++ and it sped it up by 1%, which was surprising. But yeah, that might be a way to get better throughput. But no, I'd have to be rich to just buy them. Yeah.
A few questions. So you said that you're able to model basic operation with XOR.
Mm-hmm.
You can handle anything like a free model XOR.
Yeah, I made a NAND gate. I didn't show that one, but did a 3-input NAND gate. So yeah, you could put those together and build, a whole computer out of this, which would be pretty interesting.
I guess that means that if you create this implementation, you can create kind of model on that computer.
Mm-hmm. Yeah, theoretically, good.
And then I guess another question is, from my limited understanding of quantum computation, this kind of seems to have parallels with from my understanding how quantum computation is done. If there's
Yeah. So one of the things about quantum computing is theoretically it does multiple computations at the same time. You have an algorithm, and depending on the values of variables, you'll take different paths through your code. A quantum computer might take all those paths at the same time. The closest thing to that I sort of picture with this is, the idea that all these instructions are being executed at the same time, right? So that feels a little sort of quantum-ish to me. But also, some of the stuff done with quantum suggests applications towards fault tolerance. And this does a pretty good job of fault tolerance because it's so messy, right? If I try to do an XOR and I don't set my levels exactly where they should be, it still does a pretty good job of getting the right answer. So that might be some sort of tie-in also.
I guess it also like, I think like quantum states model it from real numbers.
Yeah, yeah.
There's like kind of the karma
Mm-hmm.
it can affect because you get further away from the quantum particle.
Right. Yeah, so there might be some tie-in there. And I don't have enough experience with quantum. Every now and then, I'll go online and look at like IBM's quantum computer, and they have less classes you can take, and you can get time on their system. And I just haven't gone far enough down all of that. But yeah, that would be interesting. Yeah.
Sorry, do another one.
Yeah. Also,
Okay.
do you know about like lambda calculus?
Not a lot.
So I guess in lambda calculus, I don't know that much either, but my understanding is just one operation, one thing, the lambda function.
Okay.
Yeah, application.
Yeah.
It seems like presumably that's like a model, full model of the computation, which is like one instruction.
Mm-hmm.
Or
Yeah.
It's not really just, also like data is also just a lambda function that is constant.
Mm-hmm. So, Gerd Lesher-Bach, which I always recommend when people ask me for recommendations, pulls in a lot of lambda calculus, and Lisp is built around a lot of these ideas, and those kinds of things were brewing in the mid-'80s when my friends and I came up with the earliest version of this, which is what we call cell matrix now. And this is an attempt to take the cell matrix and generalize it, extend some of the principles of it into a higher degree. So a lot of that stuff is at some level kind of in the mix of things that led to this. So yeah, I think that's probably a key observation. Yeah.
Okay. We're in the math of this, but so with the program counter, with the program counter, you fit it to include all the real numbers. Is it so now that it's an interval of real numbers? Can you apply like properties, or can you exploit maybe like theorems, stuff like that? Have you thought about that?
Yeah, possibly.
Yeah. I mean, it is a counter, but like maybe convergence or something. I don't know. But
yeah, I mean, like space filling curves, right? So you can make a program counter that moves between 0 and 1 and gets closer and closer to any given point. And if you've got karma in there, maybe that's good enough, right? Maybe you don't have to land exactly on each point, but you can go through in some pattern and get within some epsilon. I haven't tried that.
yeah, because it's like, oh, well, if it's like, oh, I forgot what it's called, aerial analysis, where you're like, something epsilon, something delta, if it's like, if the curve is too steep, it doesn't satisfy a property mathematical.
Okay.
Maybe, or something like that, I don't know, but.
Okay.
I guess to follow up on that, have you ever considered maybe expanding it to like include complex numbers as well? And
That would be interesting.
the possibilities of that, 'cause,
That would be interesting. So, do complex numbers have a higher cardinality than reals?
I think so. It's just two reals.
It's just another plane, I think.
Yeah, it might be the same as our
Another
X.
axis.
And you can do anything. Solve any polynomial.
and you can represent, like, there's two parts now to each number, right?
What I like about that is the idea, if we're doing a two-dimensional version of doing it as a real and complex piece instead of just two reals, which is what I chose. I don't know what the advantage of that is, but it feels like there's an advantage doing it with complex. That would be interesting.
But, yeah.
That's cool.
How about like differentiating or integrating like the existence of, I guess, presumably kind of continuous.
So, I mean, I've got those equations that are trying to model what the chemical levels look like over time. and that's basically integrating, adding the effects of all of the transfers that are occurring. But I think that's the only thing I've done with trying to actually do calculus on this. Okay, yeah.
So, for the implementation side of it, where you're just normal levels with source and destination, is each, because you said that we throw out the program counters, just like counting and executing them all at the same time.
Mm-hmm.
But it's over a continuous range, so, but you did discretize it for like Python implementation?
Yeah, for simulating it.
Okay, so are you going just from left to right across each?
Well, I go from left to right, but I don't actually do any transfer until I've added up all the transfers that are being requested.
Okay.
So it should be a pretty faithful simulation, but with discretized time.
Okay, so it kind of does each one, and then it applies them all at the same time, so they don't affect each other.
They don't affect each other until we let them all go.
For one iteration, okay.
Yeah.
How difficult was it to really code some of this? It seems like one of the things that you would be staring at and just thinking about it rather than actually typing for a very long time.
It's pretty simple, actually, but the footnote or disclaimer on that is I made a lot of mistakes in the first few versions. And I would, run the system and it would flood with chemicals or all the chemicals would disappear. And it's like, well, it should be conservative, so what did I do wrong? And you'd find some, mistaken assumption or maybe just, an I instead of a J. But the actual coding of it's really not that hard. I mean, what does it take to transfer from one spot to another? Well, subtract from here, add to there. Just a bunch of arrays, pulling the chemical levels. Yeah.
So, with all these experiments, genetic alpha experiments you have you tried running them on a standard architecture?
No, but I suspect they would work just as well or better. There's been a lot of GAs for evolving logic gates, for example, or for gameplay or things like that. It's a pretty well understood technology. So my interest, and I had to keep reminding myself when I was doing this, my interest was not so much that I could run a GA to evolve exist. It was the simple fact that an exist was able to do this particular task, right? Not so much that I got there through a GA. And I realized at one point I don't really care how it gets there. I just wanted to know, is there a way to have this crazy system of chemicals that transfer and work on themselves and the ego and all of this that could actually do an exclusive OR function or drive a tic-tac-toe game and so on. And I got to the point where I was going to allow myself to play God, to peek in and see where it was in the evolution and say, oh, this individual is so close, let's just, nudge it a little bit in this direction. And I'd be perfectly fine with that because, again, I'm not really looking for, hey, look what I can evolve. I'm looking for, hey, look what this thing can do, right? So it's sort of a different task. But, that's on the to-do list. Yeah.
Do you ever, so this is right now currently like a personal project?
Yeah.
Or do you ever plan on getting maybe funding or maybe expanding? I know because you're at Clark right now, I don't know how research works.
Not a whole lot of funding opportunities through Clark.
Yeah.
Occasionally, I get the itch to go back on the road and start going to conferences and writing papers and seeing if I can draw up interest in this. And then I slap myself and I feel better. It's a hard path to go.
Yeah.
So years ago, I just switched when I want to publish, I just put it on Amazon. And, that's not a place that people are going to go for scholarly research, but if I just want to get this out there and be able to point people at it, that's what I'm doing instead of going through the regular publishing mechanism. It would be fun to have some funding, but it is so far out there, so so far from practical application, and I spent a few decades of my life trying to push cell matrix, which is a lot more down to earth. And there was some funding success, but there was a lot of, multi-day drives cross country to talk to a room with 6 people, and, that's the end of it. So, if I was 40 years younger, it would be fun. But I'm hoping somebody else might, So like I say, everything is open source. I try to put all this stuff out there, trying to reorganize the website, and, hopefully somewhere people will jump onto this and maybe carry it forward.
Isn't it sure if they, for some reason, you find out it can't actually be implemented in real life? I'm sure there's still, things in there.
Yeah.
Yeah.
I guess just out of curiosity, with the disk size on, what's the limitation on shortening that delta X as we're, and with changes that are, getting closer to, smaller real numbers?
Yeah.
How would that affect the further out? Would they make it more accurate? What are the limitations and the benefits from, getting smaller numbers?
That's a really good set of questions. I'd love you to figure that out and tell me. I've wondered about that because, when you go from discrete to continuous, things happen, right? You can get more and more discretized, and it changes some obvious things, but sometimes when you make a final leap, things get radically different, right? So right now, most of these experiments, I just take X from 0 to 40, and I do a delta X of like 0.0625. So like 16 tubes per unit nominally, so 640 tubes across, randomly picked. It seemed to have enough to make things look interesting when I plot them, but it was few enough that I could, get results in a reasonable time. But I'm willing to bet that there's probably some things that change in unexpected ways if you make it more discrete. And in the time domain, I also have no idea. It looks mostly continuous as long as your karma is low. When your karma gets high, it's interesting, it starts to look chaotic. And then the changes in time would probably be more important. But for low karma values, 3 or 4 or 5, it seems like it's moving smoothly. And so we might get, some more accuracy with a smaller delta T, but I don't know if it would really change it. The spatial domain, though, I think probably there's something there. Yeah.
For your applications, most of them are naturally things that have already been tackled by standard architecture.
Mm-hmm.
Do you think that there's applications that are more suited to this, that are that come to mind less readily?
Yeah.
Or in the computer science space that we're kind of so familiar with?
So I think trying to get a population of artists would be interesting. And you can do that, with conventional computing and so on. But I think it would be interesting to see what qualifies as interesting art from the point of view of when you feed this set of pixels into a system, the chemical levels go wild, right? As opposed to when you put this one in, they modulate a little and not much happens. Just kind of seeing what that looks like. The language thing is something I've wanted to do most of my life. There's an old sci-fi movie called Colossus, the Foreman Project, where the U.S. has a very sophisticated computer, and the computer theorizes and figures out the Soviets probably have their own version, and it asks to be put in contact with its counterpart, and they start developing a mathematical-based language to communicate with each other. And that just fascinated me. And so I always wanted to try this. And you can do this with, a couple of C programs or Python programs, see if you can share information and let them develop a way that has more fidelity, bandwidth, and so on. But I thought it would be interesting with this, partially because it seems to be a little bit more tolerant of perturbations in inputs. It's not so cut and dry what it does. And I think generally, maybe the answer to your question is things where that sort of fault tolerant is more important, might be better suited on this.
Yeah.
Yeah.
So, I guess about what, like, programming language, what this might look like.
Mm-hmm.
Like, normal programming languages seem to have, like, four, the opposite of the four characteristics of this is,
Mm-hmm.
kind of, like, subject and object, or
Yeah.
pointers, whatever, so, I think about, like, what programming language might look like, or if it would be very different.
It would be very different for sure. I optimistically made a set of beautiful templates in Inkscape, which listed all the cells and had a place for footnotes and time steps and all this kind of stuff. And I figured if I spent 5 days making these templates, that was all I needed to be able to program the system. Well, I've still got the template somewhere, but I never managed to get very far. But the way I started was, let's just put in a few chemicals. Let's just, take one small region, put some chemicals in there, and see if we can get a controlled transfer of what's happening somewhere else. And that's not too hard to do. And then let's see if we can swap the chemical levels between two locations. And if you isolate the places that you're manipulating from the code that's doing the manipulation, you can get away with that for a while. But the problem is, the feature is that, these things that I'm trying to manipulate, they're also code, right? And they're acting on other things, and eventually they start acting on themselves or on the program I'm trying to write. And yeah, so I have no idea how to address, the topic of let's figure out how to tell this what to do in some deliberate way. I don't know. I think it needs a different mindset, and I don't have that mindset yet. Yeah.
And right now, the main way to do it is you just set an initial levels and then just let it go, right?
Yeah, so with the genetic stuff, throw in some base level of chemicals, decide what your inputs look like, monitor the outputs. There's no reason that should work.
What was the role of karma in the architecture? This is like the programming on behavior.
Oh yeah. So karma says if I want to transfer from here to here, let's actually transfer from a range of locations to a range of locations. Because since these things are real valued addresses, your instruction might say, I want to transfer from location 2.563 to location 10.126, right? Well, how much stuff are you going to transfer from this infinitesimally thin tube? That felt kind of artificial to me. It feels more like if this was a real system, you'd be transferring some amount of stuff around there. And so the karma is just how much stuff do you transfer around the point that you're actually saying you want to move from and to. And yeah, it throws in some unpredictable behavior, but that's actually, with like genetic algorithms, that's actually part of what gets you your fault tolerance. Because now if you're a little bit off from that magic location, well, you're still going to do almost the same thing, right? If you go exactly from location to location and you change in the 12th decimal point, you're doing something totally different now, right? So it sort of smooths those things out. And like I say, GAs have been around for decades. And I talked to a researcher back in the early 2000s who was evolving electronic circuits using genetic algorithms. And what he did was, before he used these components to build the circuits, he radiated them. He damaged them deliberately, so he evolved circuits with damaged components. And the circuits he ended up with were more fault tolerant because of that. Because the circuits weren't always doing the same thing. So in order to be the best performing circuit, you had to be tolerant of some changes to your inputs and such. So there's ideas like that.
Another implementation thing for your karma, it kind of has this bell curve. What was the function for like?
I think it was just like an e to the minus x squared or something, for no reason except the fun function to plot.
Have you considered like trying different functions like linears and?
So I think in the Python one I'm doing linear because I was learning Python this summer and I didn't want to figure out how to do an exponent. And I wanted it to be fast, and I thought that would slow it down too much. Turns out it doesn't. So I think I just did a strict linear.
convertible. Yeah. I don't know. I guess
Like reversible?
reversible. Yeah. If after you run, sort of some initial condition, you know, some amount of time, you take the, like, inverse, and then you run it the same amount of time, and you get back to the original state.
My gut feeling is it's one of the most non-reversible systems out there. But I don't know if that's true. I'm just trying to quickly picture how I would run one of these things backwards, and it's hard to imagine. I feel like it's a many to one, like lots of different initial conditions could get to this, but I don't know. That's a fascinating question. That's going high on my list of things to think about.
Do you have a program? Yeah, I guess you will. Like when in a loop.
Yeah.
Because if you took from the destination, like you put the source of destination and the function of the conduct.
Yeah, I gotta think about that, how reversible it is. It's definitely deterministic, unless you're doing the free will stuff. But if it's many to one, then you can't reverse it.
Yeah.
That's the problem with like adding two numbers together. There's a lot of ways you can add up and get a 10. So addition is not reversible.
Like integration gets you the plus C.
Yeah, yeah.
Quick convertible, essentially you can like discretize it, put it in the matrix,
Mm-hmm. True.
figure out its property for each one, for each instance, you know, the local characterization of that matrix or something.
For some reason, I tried doing a matrix equation to describe the system before I just went to integrals. And I don't know why I thought matrices would be the right way to do it. But maybe it would be more useful as a matrix, but it was easier as integrals.
If you could reverse it, then it's only some set of possible starter conditions that you can actually know what your goal is and go backwards to get a program that works from that. That's interesting.
Cool. Well, awesome questions. Thank you. Much better. Yeah. You're welcome. Thank you so much for inviting me out here. Like I say, this has been a good excuse to kind of dust some of this stuff off, and I'd already started in the summer moving some of it into more modern frameworks. So